So let us return to this alternate biasing scheme. Last time I showed you guys this alternate bias technique, and I said, it turns out this actually has some interesting advantages. So once again, let's do what engineers do. Let's see how this works by doing the math. And in this particular case, I'm going to assume that RG is large. Okay, I'm going to set it to be a big value. And the reason for this is I want RG to be much, much larger than RD. So that is a desirable. And so I'm just picking it as a large value because it doesn't really matter how big it is, because I know that the current through that resistor is 0 because the current into the gate is 0. And also I know that the DC current through the coupling capacitor is 0. So it's really kind of irrelevant what that resistance is, so I can make it arbitrarily large. We also note that VD must be equal to VG since there is no voltage drop across RG. So when I'm talking and saying that VD is equal to VG, I'm saying the DC values, the bias values, have got to be the same. So in this case, let's find RD in order to set the drain current for this transistor to 1 milliamp. So in this case, the drain current, ID, 1 milliamp, also has to be the current flowing through the RD resistor because, once again, RG has no current flowing through it. And so therefore, 5 volts minus VD divided by RD is equal to 1 milliamp. Okay, that's one obvious equation I need. Now I need another equation. Let me ask a question. What is the operating condition of that transistor, assuming it's on? If it's on and VD is equal to VG, what do I know must be true about it? It's got to be saturated. In fact, this is effectively diode connected, even though there's a resistor there, because VD is equal to VG. And so, since VD is equal to VG, the transistor is saturated. Now, question somebody might ask, Dr. Holman, how do we know it's even on? Well, let's assume it's off. If it's off, there's no current flowing in here, so VD must be equal to 5 volts, and therefore VG is 5 volts. Obviously, it's got to be on because VG would be greater than VT. So it must be on, and it must be saturated. All right, so therefore, ID must be equal to my transconductance parameter, 2 milliamps per volt squared divided by 2 times VGS, which is just VG minus 0, minus 1. And of course, this is my threshold voltage, V sub t squared. And in this case, VG has to be equal to 2 volts. It's the only answer I get out of this. And therefore, given that VG is 2 volts, okay, and therefore VD is equal to 2 volts, I can plug it up here into this equation, and therefore what I get is that RD is equal to 3 kiloohms. So I've got a 3 kiloohm resistor required to give me a 1 milliamp drain current flowing through this circuit. All right. Incidentally, is RG much greater than RD? Yeah, clearly. Okay, 1 mega ohm is a lot bigger than 3K. So I'm fulfilling what I wanted. I wanted to make this resistor large compared to RD. Okay, so easily solved. It's biased. It actually works as an amplifier because the transistor is in saturation. I've got a coupling capacitor. I can feed the signal into the gate, and in effect, this becomes a common source topology, a simple common source topology, with the addition, of course, of that RG resistor you have to include in the small signal diagram. But the question is how well does this topology work when you consider delta VT variations? Well, let's do the same thing we did before. Let's once again assume that I've got a Gaussian distribution and I've got tolerance in that threshold voltage. So VT is 1 volt plus or minus 0.2 volts. So I'll take those same two equations I did up there. ID is equal to 5 minus VD divided by 3K, and also ID is equal to 1 milliamp per volt squared times VD minus 0 minus VT squared. And I'm now going to take those and I'm going to plug in different values of VT. If I plug in VT is equal to 0.8 volts and I solve, and notice it's two equations, two unknowns, I'll be able to solve. What I'm going to get is that ID is equal to 1.06 milliamps. VD is equal to 1.83 volts. And if VT is equal to 1.2 volts, then ID is equal to 0.94 milliamps. And VD is equal to 2.17 volts. And we note up here before VD was 2 volts. So VD moves up and down by, I don't know, say about 8% or so. ID about 6% or so for a 20% variation in threshold voltage. Not bad. This is pretty good. This is pretty good. This is a fairly stable bias point. Certainly compares just as well to what we looked at before. So it turns out that this actually is a pretty good tolerance-resistant bias technique. So you will actually see this, and it's a very simple biasing technique. The drawback to this is you don't necessarily get a lot of dynamic range out of the design. So it's not an amplifier that gives you large swings at the drain voltage. But it still is a pretty simple and pretty easy and very, how should I say, very tolerant design. And notice I didn't need to use any kind of bypass capacitors or any type of source degeneration resistors. So this is just a useful technique, an alternate biasing technique that people will use. All right? Questions about this? All right, so let's now consider yet another biasing technique. And this one I would say is probably going to be one of the more interesting and certainly one of the more common techniques. And this is current source biasing. And when you look at high-performance circuit designs, you're almost always going to be using some variation of this type of bias technique. Let's take my same circuit I was looking at before. Okay, so this is the same circuit before where I had the RS, the source to generation resistor in it. And before we had a source to generation resistor here which we could bypass. But obviously you still get some variations in drain current because, you know, even if you make RS bigger, you're still going to see some influence due to the effect of threshold voltage variation, not to mention the tolerances of the other resistors in the circuit. Is there a way we can make that bias point even more stable? Yes. Current source biasing. Specifically, if I wanted ID to be exactly equal to 1 milliamp, as I chose for my previous design, what if I could do this? What if I could actually put a current source into that circuit, into that drain leg? If I did that, it doesn't matter what the other voltages are going to be or what the other variations in resistances or in transistor parameters would be, because the drain current is set by that current source. So in this case, if VT were equal to 1 volt, and I'll just call this voltage, of course, Vs at the source, if VT is equal to 1 volt, Vs is equal to 1 volt. If VT is equal to 0.8 volts, then Vs is equal to 1.2 volts. And if VT is equal to 1.2 volts, Vs is equal to 0.8 volts. But in every case, ID is fixed. So it doesn't matter. I can move those voltages around. As long as, keeping in mind, a current source doesn't care what voltage is across it, an ideal current source, then as long as that's true, this current source gives me a totally stable bias point. All right? The question is, how do you make a current source? Well, I'd say that's a good question, but we've actually answered that question. We've looked at this earlier on. What did we say about transistors, MOSFETs, and saturation? What do they behave like? Current sources. What do bipolar transistors and forward active behave like? Current sources. We saw that in the curves we did before, where once we got out to that saturation or forward active region, the current remained the same, even if we changed the voltage across the collector and the emitter or the drain and the source. So if I want to make a current source, I can't pull an ideal element out of a box, but I can certainly create a current source using a second transistor. Now let's consider how we would do that. So what I'm doing here is I'm going to add a second transistor with its own bias network. Call this M1. I'll call this M2. By KCL, ID1 and ID2 must be the same. So M2 sets the current for M1. And notice what I'm doing here. I'm doing nothing except just taking a standard transistor and then adding its own resistors here in order to create this current source effect. So this portion here becomes my current source. Turns out that works incredibly well. In this case, the drain current is as stable as we can make it by using M2. So the more stable we can make that, then the more stable the M1 current is going to be. We note M2 must remain in saturation. That is absolutely essential. Not only M1, but M2. They both got to be saturated because, keep in mind, if this thing goes into triode, it quits acting like the current source. It becomes more like a resistor. So a second transistor actually gives us now a very stable bias point. All we really have to do now is focus just on making this stable, and the rest of the circuit, we're fine, because this is going to set the drain current. There's only one tiny problem with this circuit. Let's assume I've got my input here. And here's my output. If I were to build that amplifier and put that transistor in and select a couple of resistors to set my current for this, what would my gain of this amplifier be? Anybody can kind of give me an idea what you think it would be? Let me give you a hint. This is a current source. What is the resistance seen looking down into the drain of M2? Is that going to be small or is it going to be large? That's acting like a current source. So what's it going to be? It's going to be big, okay? In fact, what you're going to see here is little r sub O2. You can do the small signal diagram yourself and check that. The resistance seen looking into the drain is simply going to be set by the r sub O, which is going to be big. So I've got effectively a very large source resistance for M1. What is the gain going to be if the source resistance is huge? Keeping in mind that the gain of M1 is going to be equal to effectively minus RD over RS. And RS is therefore equal to RO2. What's that gain going to be? Just about 0. Okay? You're not going to get any gain out of it because you've got this huge, effectively huge source resistance introduced by the fact you're now putting in a current source. Many times over the years, I've had students come from the lab and say, Dr. Holman, my amplifier's not working. And I'll walk over there and I'll look, and they're missing a component. What did they forget to include in that circuit? Bypass capacitor, exactly. If you're going to use this trick, you must add a bypass capacitor. So DC-wise, the capacitor has no effect on the biasing, because that's all DC. But in the small signal, in AC, now that source is grounded. And now you get a working amplifier again. So we note C sub B must be added to the circuit. So if I want to restore my AC gain using current source biasing, then I've got to have a bypass capacitor. Well, No surprise here, when we had a source resistor there, we bypassed it, right? Same thing here, except now I'm using a current source, DC current source, but still I'm bypassing it. Now, looking at this design, you'll look at this and say, well, hopefully you're looking at this and saying, well, Dr. Holman, aren't you simply taking the problem we had in M1 and pushing it off to M2? I mean, don't you have the same issues with delta VT and everything else in M2? Have we really solved this problem? Well, that's a good point. This is not necessarily a good way to deal with creating a current source. There are better ways to make current sources. Let's talk about one of those right now. And we're going to talk more about this later on in the semester, but I'm going to briefly mention it to you right now. If I want to create a current source, here is the most common way you'll see people do it in IC design, using a technique called a current mirror. What's a current mirror? Well, as we're going to see, we need yet another transistor. In this case, I've now added a third transistor, and I'm going to call this M2, and this, I'm going to call this M3. All right? So now I've got this. This is now my current mirror. And notice all I'm doing here is I'm replacing this now and putting in this. All right. Call this resistor R bias. And for these two transistors, I'm going to make an assumption. I'm going to assume that M2 and M3 have identical parameters except for having different width to length values. They have different geometries. So I'm going to say this has W2 over L2 for M2, and this has W3 over L3 for M3. How do I get two transistors with identical parameters? How do I make that happen? Well, one way is I can just start sorting a lot of transistors and could sort through a few thousand or a few million until I find two that are perfectly matched. But there's an easier way to get transistors that have identical parameters. And that is to make sure that we manufacture them both at the same time, on the same die, under the same manufacturing conditions, and we put them right next to each other. So whatever one transistor is exposed to during the manufacturing process, the other one is also exposed to. If you do that, then you have what you call two matched devices. So you can match M2 and M3 by manufacturing them on the same integrated circuit. And in fact, this is done all the time. In fact, as we're going to see later on, this is one of the mainstays of modern IC design, the idea of utilizing matched devices. So this is not something you can do discreetly very easily. It'd be very expensive and difficult to do. But on an IC, it's trivial. As long as they're manufactured right next to each other, okay, then we're fine. Now, the nice thing about this is the VTs can vary, but they vary together. All the other parameters vary together. So we don't really care so much what the parameters are as long as they track each other between those two transistors. So, in looking at this, let's consider what we've done here, okay? Now we note M3 is diode connected. We're already requiring that M2 remain in saturation, and we also know that M3, if it's on, is going to be in saturation as well. So if it's turned on, it's saturated. We know that to be true. We also can see that the way I have these things connected, both those transistors are connected to the same gate, the same source nodes. So VGS is the same for both transistors. So let's go through here, and I'm going to assume there's some current Iref flowing through R bias, which in turn is going to flow through M3. The gate currents are equal to 0, so there's nothing to worry about there. I know that ID3 must be equal to Iref. So in this case, I know that Iref must be equal to ID3, which is equal to K prime N over 2 times W3 over L3 times VGS minus VT squared. And I also know that ID2 is equal to K prime N over 2 times W2 over L2 times VGS minus VT squared. And we note I've got the same VT and the same K prime values for both transistors. And that's because they're matched. So whatever variations I have is going to be the same between those two transistors. And therefore, if I look at the ratio of ID3 to I2, that's equal to the ratio of Iref times ID2 is equal to K prime N over 2 times W3 over L3 times VGS minus VT squared divided by K prime N over 2 times W2 over L2 times VGS minus VT squared. And when we look at the ratios of those two currents, very conveniently, the K prime N over 2 terms cancel out. The VGS minus VT squared terms cancel out. In other words, the ratios of the currents of those two transistors is strictly a matter of geometry. Therefore, I know ID2 must be equal to Iref current, whatever that is, multiplied times the ratio of the ratios of the width-length ratios of the two transistors. So what do we do then? What we do then is we simply pick a value of our bias to sit Iref. So in this case, it's just going to be, you can calculate that yourselves. You can actually go through and decide and calculate for yourselves very quickly. If I want to set ID, you actually have done that problem before in your homework. So if you want to set ID3, all you have to do is pick the right value of R bias to do that, given the transistor parameters. All right? So this is a much better way to take these two to set this bias current, because now, because of the matching, I can tolerate variations in those M2 and M3 transistors. Now, of course, I'm still having to deal with the resistor, the R bias, and it turns out that there are even more sophisticated tricks people use in order to make the bias even less sensitive. So, for example, using techniques like band gap references and things like that, which are, quite frankly, unfortunately, beyond the scope of this course. But in more advanced analog design courses, you can learn more tricks about how to make biasing even less sensitive and make it more stable over all operating conditions. But this trick here, notice, not only am I improving the bias, what else am I doing? I'm also getting rid of extra resistor, right? I went from 2 resistors now to 1 resistor. So it turns out that this also, it's always a good idea to sacrifice a resistor or remove a resistor and replace it with a transistor. Transistors are small. Resistors are big. So from an economic point of view, transistors on integrated circuits are always a better choice than actual resistors or capacitors, physical devices. All right? Once again, if I'm going to do this little trick with the current mirror, what must I not forget? The bypass capacitor. Because once again, I'm looking into a transistor here, M2, which is once again operating in saturation. I'm just going to see RO2 looking down into that transistor. So when I tell you guys that transistors behave like current sources, I mean that. They're going to have high resistance, high impedance looking down into it. Because, of course, current sources have infinite resistance, ideally. So the same kind of idea here. All right. Notice, of course, for this circuit here, all the transistors must remain saturated for this trick to work. So that's one thing you obviously have to watch out for. If you push any of these into triode, or certainly, for example, if M1 or M2 gets pushed into triode, then obviously that's not going to work. But everything needs to remain in saturation. All right. We're going to come back to this later on. We're not going to leave this current mirror technique behind, because it's worth pointing out to you guys, there is still something very wasteful I'm doing in this design. And what is that? I'm using a capacitor. I've got to use that big CB capacitor. It's got to be large in order to set the impedance of that source to ground. Wouldn't it be nice if somehow I could get rid of that capacitor? Well, we're going to come back to that later on. Turns out there are ways that we can use in order to have the advantage of a bypass capacitor without actually physically putting a bypass capacitor into the circuit. So we'll talk about that later on when we look at circuits that are used on integrated circuits, IC amplifiers. So that'll be on the final exam and on the last homework assignment. Okay. So questions about any of this? Okay, well, I want to very quickly also talk about BJT biasing, which has a lot in common with what we saw here with the MOSFET biasing, but one important difference is in a BJT we have to deal with the fact we have a non-zero base current. So let's consider that. Let's talk about practical BJT biasing. Okay, so if we were going to bias a BJT, let's go ahead and let's do something very similar to what we saw with the MOSFET. What if I did something like this? Very similar to the BJT, or pardon me, with the MOSFET, except I put in a BJT in place of the MOSFET. If I tried to bias a circuit up this way, would it work? If I went into the lab and tried that, could I bias that transistor up and make it stable? Well, let's think about this. If the emitter is grounded, then the base has to be somewhere between, say, 0.6 volts to 0.7 volts. Except there's only one little problem. IC is equal to ISE to the VBE over V sub T, thermal voltage. I've got an exponential relationship between IC and VBE. So IC is a function of E to the VBE, which means the tiniest variations in base voltage are going to create huge swings in current. A few millivolts, and I can have an enormous swing because of the exponential relationship. Well, obviously, there's no question that this is going to happen. So this type of biasing for a BJT, where I just connect the emitter to ground, just doesn't work. I can make it work with MOSFETs, although I'll have bias point variation, but I can still make it work because that's only a square variation between VGS and ID. But here I've got an exponential variation between IC and VBE. So this is not going to work. Not practical. What do we have to do for this circuit? What is it required? What must we add to this circuit? I've got to add an emitter generation resistor, right? For the MOSFET, it was an option. It improved the bias point. Here, it is a requirement. I cannot build anything that even resembles a stable bias point unless I add R sub E. I've got to have emitter degeneration. No option. So if I'm going to use this type of biasing where I'm going to have a voltage divider at the base, then R sub E is necessary. So here is what we're going to need to draw. Let's draw a circuit, and let's take this topology, and I'm going to add an R sub E, and I'm going to put in some values. So in this case, I put in a 100 ohm emitter degeneration resistor. And for these two resistors here in the base leg, I just kind of arbitrarily picked some big values, 400K and 100K. And I'm not saying necessarily that any of these are optimal resistor choices. I'm just picking a couple of resistors. And I'm just going to pick some values and do some calculations and see how well this circuit works. Okay. Now, in a transistor, transistors are going to be sensitive, first of all, to changes in beta. Beta varies, the current gain. So that's going to change. And also, to changes in temperature. And why is that? Okay. Well, keep in mind, there is a diode between the base and the emitter. There's a p-n junction. And we talked about this before. There is a relationship, a temperature coefficient, a temperature dependency of -2 millivolts per degree C for the voltage across a p-n junction given constant current. So what I'm going to do is I'm going to solve for the bias point of this circuit, and then we're going to look and see what happens as we move these operating points around. So we move the temperature and we change the beta of this transistor. So let's assume that beta is equal to 100 plus or minus 50. Let's assume my nominal value is 100, but I can go anywhere from a beta of 50 to a beta of 150. 50 is still reasonably large. Question is what's that going to do to my biasing here? Well, let's go through and let's do some calculations here. What I'm going to do here is I'm going to use the little trick the book talked about here. What I'm going to do is I'm going to, just to simplify our analysis, I'm going to first convert this circuit into its Thevenin equivalent. Just use the book technique in order to make our analysis a little bit simpler. So if I've got just a voltage divider connected to 10 volts, I can very quickly do the Thevenin equivalent for that. And if I do, I will draw this up here. I'll get the following. Okay, so when I turn my base voltage into its Thevenin equivalent, I wind up with a 2-volt source and an 80K resistor. So of course that 2 volts is just the open circuit voltage here at the base with everything disconnected, 100 over 500 times 10, and then the 80K is 100K in parallel with 400K. So just Thevenin's equivalent. So I wind up with this circuit. And at this point, I'm going to assume that RC and the RC value is going to be sufficient such that my transistor is going to remain in forward active. So I don't know what that RC value is, but I'm just assuming I'm picking it in such a way that I don't push the transistor into saturation. I'm not making it too large. But assuming that's the case, then I can now go through and I can write a little KVL equation around this mesh, around this loop, or I'm sorry, yes, around this loop or mesh. So 2 volts is equal to, well, in this case, I've got IB flowing into the base. I've got IE, this voltage is VE, that voltage is VB. So I'm just going to add those to that circuit, and then I'm going to write my equation. So in this case, going around this loop, then 2 volts is equal to, in this case, 80K times IB plus VBE plus 100 times IE. IE will be equal to beta plus 1 times IB. Now this is sufficient now for me to go through and solve through the circuit. So I'm going to assume that VBE is equal to 0.7 volts. So I'm going to assume this is stable, but now I'm going to vary beta. So in this case, let's go ahead and let's look at our different values. If beta is equal to 50, then VB will be equal to 0.778 volts. IB is equal to 15.3 microamps. And IE is equal to 779 microamps. If beta is equal to 100, then VB is equal to 0.846 volts. IB is equal to 114.4 microamps. And IE is equal to 1.46 milliamps. And if beta is equal to 150, then VB is equal to 1.31 volts. IB is equal to 13.7 microamps. And IE is equal to 2.06 milliamps. Is that a particularly stable bias point? I'd argue it's not that good. Okay, I mean, it's not going all over the place, but clearly I'm getting a pretty significant amount of variation with beta. Let's now look at this same set of equations. And now let's look at it from a different point of view. Now let's assume beta is 100. Let's let beta be stable. But now I'm going to look at VBE. I'm going to assume VBE is affected by temperature. So I'm going to assume that delta VBE with respect to temperature is about minus 2 millivolts per degree C. We talked about that several weeks ago when we were looking at PN diodes. Well, now it's coming back and we have to think about it. Now, I'm doing this, I'm keeping one stable while moving the other just because I'm trying to make the problem less complicated. I'm just trying to show the effects in both. So if the beta is stable but the temperature changes, then in this case, let's assume that temperature is equal to some nominal temperature plus or minus 50 degrees C. So whatever operating temperature I'm at, I'm going to assume that it'll either be hot or it'll be cold while this circuit's operating. So VBE is equal to 0.7 volts at my nominal temperature. All right? So I'm assuming that 0.7 volts goes for VNOM. And so in this case, I'm now going to, using beta equal to 100, I'm going to plug into this equation, only now I'm going to change VBE. So in this case, what I'm going to get is 50 degrees C. What I'm going to see is that, therefore, delta VBE is going to be equal to plus or minus 100 millivolts, assuming everything else remains the same. Over a 50-degree swing, 2 millivolts per degree C, I'll expect to see a 100 millivolt swing. So therefore, my temperature VBE is going to be equal to 0.7 volts plus or minus 0.1 volt. Let's now take this, plug it into this equation here. And what we'll get is at T nominal minus 50 degrees C, VB is equal to 0.935 volts. IB is equal to 13.3 microamps. And IE is equal to 1.35 milliamps. At T nominal, VB is equal to 0.846 volts. IB is equal to 14.4 microamps. IE is equal to 1.46 milliamps, which of course is exactly the same value I got up there, right? Beta is equal to 100 and the temperature was 0.7, so the same value. And at T nominal plus 50 degrees C, then VB will be equal to 0.757 volts. IB is equal to 15.5 microamps. And IE is equal to 1.57 milliamps. And that's just due to the temperature variation, assuming the beta remains stable. So up here, I just moved the beta and assumed VBE was a constant. Here, I assumed the beta is a constant and just changed VBE with temperature. But in a real design, it's even more sensitive, it's even more difficult than this because it turns out beta is also a function of temperature. Other transistor parameters and the resistor values are also going to be subject to tolerances and to environmental parameters. So it actually becomes a lot messier even than this. But clearly, these choices I made for this circuit weren't necessarily the best, given the amount of variation I'm seeing here. Let's think about this for a minute. If I wanted to make the bias point more stable, what could I do to the value of RE? I'd make it bigger, right? Obviously, if I make RE larger, okay, we saw this before with the MOSFET. As it gets bigger, what we're going to see is changes in delta VBE are going to have less and less effect on the bias point. So we can improve the biasing. I can improve bias stability by increasing RE. That's one thing I can do. I also made another kind of intentional design mistake here too. So I'm going to call this current IB1, IB2, and IB. Actually, I'm going to call these different names. I'm going to call this IR1 and IR2. I don't want there to be any mistake about them being anything but resistor currents. I'll call these IR1 and IR2. So if I were going to write a KCL equation, what would it look like? Well, 10 minus VB over IR1 must be equal to IB plus VB. I should say this is, take that back. I'll call this R1, excuse me. Actually, I'm making this, yeah, let's do it this way. Let's do it this way. This R1, that's R1, and this is R2. There we go. So 10 minus VB over R1 is equal to IB plus VB over R2. And so, of course, in this case, this is just equal to R1, and this is equal to IB plus IR2. This would be a voltage divider, except for one minor flaw in this voltage divider. IB. As base current is pulled out of this node, it changes the value of VB. It can't help but change it, right? KCL tells us that. But what could you do if you wanted to minimize the effect of IB on VB? What could you do according to this equation? What would be the smart thing to do? What if we made IB small relative to IR1 and IR2? Then changes in the base voltage will be small, will be reduced. So if I change the base voltage, then delta VB is going to be small. Effectively, I'm simply making this a negligible amount of error. So what can I do here? Well, IB is going to be a function of the collector and emitter currents of the transistor, which I got to set for a bias point. So I may not be able to do much about IB, but I can certainly do something about IR1 and IR2. So another way to look at it let's make R1 and R2 smaller so as to increase IR1 and IR2. So it turns out there are two things I could have done to make this circuit more robust. I could have made the emitter resistor larger, And I also could have made these resistors smaller. Instead of, why did I say 400K and 100K? Why not 40K and 10K? Or what about 4K and 1K? If I chose those values, the currents flowing through the resistors would be larger, and the base current would be a smaller error to that voltage divider equation. Why not do that? Okay, these two things. Turns out that these are incorporated into something called a rule of thumb, okay? Let's incorporate these two techniques into two ideas that people will tell you are a good idea to use for BJT biasing. So some rules of thumb for BJT biasing. First of all, set IB1 so that it is much, much less than IR1. Okay, the current that was flowing through that base resistor, and the resistor in that base bias circuit. So in other words, I want IR1 to be approximately equal to IR2. I want these currents to be large enough so that the base current is essentially a negligible error. And therefore, this current is approximately equal to that current. That's what I want. Therefore, choose R1 and R2 such that within the range of about 0.1 to IE. IR1 is about anywhere from 1/10 to the same value as the emitter current we're trying to design for. And once again, this is just a rule of thumb. Or I want my emitter resistor to be much, much greater than the equivalent base resistance. So when I did that Thevenin problem over here, when I took that RB, the RB was equal to R1 in parallel with R2. So I want this to be equal to RE is much, much greater than R1 in parallel with R2 divided by beta plus 1. That's another way to accomplish it. But really, this is what you want. Secondly, second rule of thumb, set VB approximately equal to 1/3 VCC and VC approximately equal to 2/3 VCC. And this makes, in this case, this makes VB much, much greater than VBE, which minimizes variations due to changes in delta VBE. It's called the rule of thirds. So the idea behind this is it gives you a reasonable compromise in stable bias versus reasonable output dynamic range. So if we were going to do this rule of thirds and we were going to apply this, let's redesign our circuit. Here is a much more robust BJT design. I'm going to assume here I've got 12 volts, and in this case I want to bias for a milliamp for the emitter current. So I'm going to apply these two bias techniques. First of all, the rule of thirds. I've got 12 volts. VB is going to be equal to approximately a third of that, 4 volts. So I'm going to set that to approximately 0.4 volts. The collector voltage is going to be 2/3. That's going to be equal to 8 volts. That's a deliberate design choice on my part. So if I do this, I now have to go through and pick some values. So in this case, I'm also going to make R1 and R2 small so that the currents flowing through them are large. So in this case, I've got 12 volts. I want a milliamp here. So I'm going to assume I'm also going to have, say for example, a milliamp in this base leg. I'm going to assume that this current is going to be about a milliamp. And if that's the case, and this is about 4 volts, that'll be 8K, and this will be 4K. That won't be exactly equal to 4 volts. The base current will still have an effect. We'll have to figure out what that effect is going to be. Here's our base current. And now this will be equal to 8 volts, 12 volts. I've got about a milliamp flowing through it, so this is going to be 4K. Since IC is going to be approximately equal to IE. So I'm going to assume that's going to be about 4K. And if this is going to be 4 volts, then this is going to be 3.3 volts at the emitter. Assuming, once again, 0.7 volts, base emitter, 1 milliamp, and this is 3.3 kilo ohms. So this is a circuit that is biased according to those two rules of thumb. I've made this current large so that the base current is going to be small. And I have made RE large enough, and I've put these voltages at about 4 volts and 8 volts. All right, so let's go through, and if we were to now to actually go through and do the same thing we did before. We said let beta equal to 100 plus or minus 50, and also to let VBE equal to 0.7 plus or minus 100 millivolts. Due to temperature. And I were to do exactly the same analysis I did a minute ago. I'm not going to bother to go through it, but if I were to do that, what I would get is the following. Due to delta beta, IE would be equal to 984 microamps up to a maximum value of 995 microamps. If I were to do my temperature due to the change in temperature, which changes VBE, then what I would get is that IE would range from 962 microamps to 1.02 milliamps. So that's now my bias variation over changes in beta and changes in temperature, which in turn change VBE. Is that a pretty stable bias point? Yeah, that's pretty close to the 1 milliamp I wanted. It doesn't move very much. And I'm basically turning a lot of knobs in order to try to change the bias point of that transistor. So I'm applying these two rules of thumbs, and I get this much, much nicer biased circuit. So what's the drawback? Well, I'm biasing the collector at 8 volts. Okay, which means I don't have, I'm sacrificing some dynamic output range. How low can that collector voltage go before I start hitting saturation for this transistor? It can go down to the base voltage, about 4 volts, or it can go up to 12 volts. So I've got a dynamic range of about plus or minus 4 volts. So we notice our dynamic output range. So that's not bad. I mean, I could get a more dynamic range, but I would sacrifice bias stability. But it's not bad. It actually works pretty well. Okay? So this is, once again, very, very common technique, this idea of the rules of third and also making the bias, the current flowing through this base string fairly large. You don't want to use large resistors. You want to use smaller resistors. Okay? All right, so next time we'll very, very quickly look at the other biasing techniques for BJTs, which are very much like what we already saw with MOSFETs. And then we're going to move into one of the more interesting little sections. We're only going to spend a lecture on it. And we're going to talk a little bit about digital integrated circuits and how we use transistors in digital circuits and what is interesting about them. And of course, this is very relevant to the lab you guys are doing this week. So we'll finish things up for exam 2 next lecture.